Some questions you probably turned over late at night. Like, that decision you just made. Was it really you making it? Or was it written into the universe from the very first instant? Push a little further, and it gets dizzier. Maybe the future hasn't yet to happen at all. Maybe it already happened, and we're just moving through it, frame by frame, like passing along a track that's already been laid. Two more questions, asked again and again in recent years. The cause and effect we take for granted, could it be just a large-scale illusion? And the one that really keeps you up at night, could we, all of us, simply be living inside a simulation run by some far more advanced civilization? This episode doesn't dodge these questions. But let me be upfront. Physics genuinely can answer them, as long as you're willing to sort the answers into three kinds. The first kind, confirmed by experiment over and over, almost impossible to be wrong. The second, serious, beautiful, but still at the frontier of conjecture. The third, questions that no experiment today, and perhaps no experiment ever, can settle. Those are really philosophy. Keep these three layers straight, and you'll find the real answers are far more interesting than the clickbait headlines. So this time, we follow the evidence. From the two hardest cornerstones we have, all the way out to the edge of space-time, and that ultimate question about the simulation. Ready? Let's begin. First, the two hardest things we've got. The first cathedral is general relativity. In one line, matter tells space-time how to curve, and space-time tells matter how to move, all packed into this single equation. And it's no armchair theory. From the precession of Mercury's orbit to 2016, when humanity first directly heard two black holes merge as gravitational waves, to the Event Horizon Telescope's image of a black hole's shadow, it has delivered again and again. By 2026, the catalog of recorded gravitational wave events stands at about 390. The loudest of them, GW250114, even directly confirmed Hawking's black hole area theorem. This cathedral is frighteningly solid. The second cathedral is quantum mechanics, and the quantum field theory and standard model it forms together with special relativity. Its worldview is completely different. A system state is a vector in Hilbert space. When no one is looking, it evolves unitarily, deterministically. But the moment you measure, all that's left is probability. Its most counterintuitive cornerstone is Bell's inequality. It says, any theory that is local, with properties fixed in advance, cannot push a certain correlation past 2. Yet quantum mechanics reaches 2 root 2. The loophole-free experiments of 2015 nailed this shut, and the 2022 Nobel Prize in Physics went to exactly this work. Let me underline just how solid these two cathedrals are. Quantum electrodynamics predicts the electron's magnetic moment to more than 10 decimal places, matching experiment perfectly. It is the most precisely tested theory in human history. On the relativity side, the 2017 neutron-star merger pinned the speed of gravity to the speed of light, to a part in 10 to the 15th. So what we're about to challenge isn't two shaky theories. It's two cathedrals whose foundations run frighteningly deep. And one honest aside, a couple of the anomalies that made big noise these past years, like the muon G-2 by 2025, as the theory side improved, actually came back into line with the standard model. You see, the cracks sometimes shrink, but here's the rub. Each of these cathedrals is staggeringly correct, yet they're built on foundations that don't fit together. General relativity is deterministic, local, with spacetime itself the dynamic lead actor. Quantum mechanics is probabilistic, carries non-local correlations, and runs on a fixed background stage. Try to quantize gravity the way you quantize the other forces, and the math instantly breaks. It's non-renormalizable, needing infinitely many correction terms to cancel the divergences. And this crack tears wide open in exactly two places. One is the singularity. Penrose and Hawking proved that general relativity predicts its own breakdown. At the core of a black hole, and at the Big Bang, curvature diverges to infinity. The other is the black hole information paradox. Hold on to these two rips. Almost every late-night question in this episode crawls out of right here. But before we dive into the unsolved mysteries, Let me ask you to stop and marvel for a moment. Because these two cathedrals, even their most solid, most thoroughly tested parts, describe a world already bizarre beyond all everyday sense. Remember, this whole stretch, every phenomenon in it is confirmed, measured, and reproduced again and again. They're quietly telling you something important. Bizarre has never meant unproven. Start with time. In relativity, time isn't a uniform background that flows the same for everyone. It genuinely slows down with speed and with gravity. This isn't philosophy, it's engineering. The GPS in your phone has to correct every single day for the tiny mismatch in time between the satellites and the ground, or your position would drift kilometers off within hours. In 2022, scientists at Gila, using an atomic clock of strontium atoms, measured a difference in the rate of time across a height of just 1 millimeter, to a precision of 1 part in 10 to the 20th. Time runs differently from place to place and speed to speed, and that fact is as hard as they come. And once time is different for everyone, a more vertiginous consequence follows. There is no single now that the whole universe shares. Your now and the now of someone far away moving fast relative to you are two different slices that don't line up. What counts as simultaneous has no universal answer, and this one matters, so we'll come back to it in detail later. Now, mass and energy. Einstein's most famous equation, E equals mc squared, says something staggering. Mass is a hugely concentrated form of energy, and the two convert into each other. Every second, the sun turns about 4 million tons of mass straight into light and heat. When a particle meets its antiparticle, they annihilate completely into pure energy. And the reverse is even more interesting. Most of your body's weight does not come from the rest mass the Higgs hands out, but from the seething, strong force binding energy holding the quarks inside your protons. In a real sense, you are frozen energy, then gravity. We all think of gravity as a force, but general relativity says it is nothing of the kind. It's the geometry of spacetime, bent by mass and energy. You stand firmly on the ground not because Earth is pulling you, but because Earth has dented the spacetime around it, and you are simply taking the straightest possible path through that curve. Push the bending to the extreme, and you get a black hole's event horizon, a one-way border of no return. Inside it, not even light escapes. And from far away, an object falling toward the horizon seems to slow more and more, as if frozen forever at that edge. In 2019, the Event Horizon Telescope took the first picture of that border, cut to the quantum side, and the strangeness only thickens. First, wave-particle duality. An electron, an atom, even a large molecule can be counted one by one like particles, yet also pass through a double slit like a wave and interfere with itself. And this isn't a privilege of tiny specks. In 2025, physicists got a nanoparticle of more than 7,000 atoms, weighing about 170,000 daltons, to show interference fringes too. Second, the uncertainty principle. The product of the uncertainties in position and momentum can never drop below h-bar over 2. And mind you, that's not because our instruments are clumsy. It's that the particle simply does not possess a definite position and momentum at the same time. Third, superposition and collapse. Before it is measured, a quantum system can sit in a superposition of several states at once. That's what Schrödinger's both dead and alive cat means. Yet the instant you measure, only one outcome remains. Fourth, entanglement. Two particles can be correlated so tightly that measuring one instantly fixes the other, even half a universe apart. Einstein found it so unsettling he called it spooky action at a distance. But don't be misled, it still cannot send any information faster than light. The deeper meaning of these two is the star of the next few sections. Fifth, quantum tunneling. A particle can pass straight through a wall it could never, by classical mechanics, climb over. And this is no parlor trick. The sun shines because protons tunnel through the wall of repulsion between them to ignite fusion. Alpha decay, the flash memory in your phone, the scanning tunneling microscope. all run on it. What's even more interesting, even the question of how long does it take to cross that wall is still argued at the frontier. The latest attosecond experiments clock it at the scale of 100 attoseconds and still can't give a final answer. The last two pull us straight into the deep water ahead. One is quantum fluctuation. Even a vacuum, empty of everything, is ceaselessly, spontaneously popping pairs of virtual particles in and out of existence. The vacuum is never truly empty. The other is wormholes. They are, in fact, a perfectly legal solution of general relativity's equations, a bridge in spacetime joining two places. Only to make one actually traversable, you need a kind of exotic negative energy matter, and we simply can't produce enough of it. That quantum chip experiment a few years back, hyped as making a wormhole, was really just a badly overread simulation. But between wormholes and entanglement hides the most fascinating thread of the decade, and we'll get to it very soon. All right, marvel over. But hold on to what this whole stretch is saying. Every strange thing above is a fact, confirmed again and again. And even so, they've shattered our everyday intuition to pieces. Next, we step from this known strangeness into the truly unsolved strangeness. And the first question we'll take on is the oldest one of all. Is the future really already written? Start with the oldest question. Is the future already written? In the 19th century, Laplace imagined a demon. If it knew the position and velocity of every particle right now and could compute infinitely fast, then past and future would both be fixed, calculable in a single stroke. In classical mechanics, and even in general relativity, given the initial conditions, the future is completely locked in. That is determinism. Quantum mechanics punched the first hole in that picture. It has two sets of rules. When no one's watching, the wave function evolves by the Schrödinger equation, unitarily, deterministically. But the moment you measure, what you get is only a probability. The same initial state can collapse to different outcomes. So the question becomes, is this randomness truly random? Or are we just missing some hidden variables? Einstein bet on the latter. God does not play dice. And behind it all, there must be something definite we just can't see. And Bell turned that bet into an experiment you can actually run. He proved, if the world really is local, plus properties fixed in advance, that correlation could never exceed 2. But quantum mechanics predicts it reaches 2√2. Run the experiment and it sides with quantum mechanics. In 2018, researchers even used starlight from quasars billions of light years away to choose the measurement settings, pushing any cosmic conspiracy loophole back nearly 8 billion years. So Einstein's kind of local hidden variables is ruled out. That part is confirmed over and over, but pay close attention to what Bell actually says. What it rules out is the combination of two assumptions, locality and realism. It does not force one single worldview on you. So the path forks, the many worlds interpretation, and Bohm's pilot wave theory actually bring determinism back at the price of infinitely many parallel branches, or an explicitly non-local guiding equation. While objective collapse theories say the collapse is a real, physical, random process, testable, just with no deviation detected yet. In other words, is the world deterministic depends today on which interpretation you believe, and they all give identical experimental predictions. In recent years, physicists have pushed this even sharper. The so-called extended Wigner's friend thought experiment, plus a no-go theorem from Frotziger and Renner in 2018, proved something startling. Observer-independent objective facts, locality, and a quantum mechanics that also holds for the observers. You cannot have all three at once. Meaning, even whether two different observers can share the same objective fact is starting to look doubtful, which tells us this determinism question is hard not just because we aren't clever enough, but because the very foundations of quantum theory are far stranger than intuition. And one point that's constantly confused, which we must pull apart, determinism does not equal predictability. A chaotic system is strictly deterministic, yet so sensitive to its initial conditions that long-term prediction is simply impossible. There's also a more radical escape hatch called superdeterminism. If you're willing to assume the experimenter's choices were secretly correlated with the system's hidden variables all along, then Bell's theorem can be sidestepped at the cost of accepting a kind of conspiratorial fine-tuning which Wood and Speckens proved it requires. It's not logically refuted, but it's always been a tiny minority view. So, back to the question, does physics say everything is already destined? No. It also hasn't proved you have free will. What it really confirms is just two things. Local realism is false, and entanglement, however eerie, can never send a signal faster than light. As for, is the future already written? Up to here, it is a philosophical question, no consensus and no way to decide. So let's ask it differently. Could it be that the future doesn't lie ahead about to happen, but has already happened, laid out there, and we're just passing through it? This idea comes straight from special relativity. Simultaneity is relative. For an observer moving relative to you, their slice of now is tilted. Their present might contain your past or your future, which means there is no universal now that everyone shares. Push that to its conclusion, and you get the so-called block universe. Time isn't a flowing river, but a single four-dimensional whole, with past, present, and future all equally real, laid out together like a strip of film already shot. In this picture, flow and this moment may not be fundamental features of the world at all, just an experience of our consciousness. But we plainly feel that time has a direction. That direction physics calls the arrow of time, and it comes from the second law of thermodynamics. Entropy increases. The eerie part is that the microscopic laws are almost perfectly time-symmetric. Run them backward, and they still hold. So where does the arrow come from? The standard answer today is a boundary condition called the past hypothesis. Our universe started in an extraordinarily low entropy, highly ordered state. Why it was so ordered to begin with is itself an unsolved problem, tangled up with cosmology and quantum gravity. By the way, the block universe isn't the only reading either. Some argue for a growing block. The past and present are real, but the future hasn't become real yet. Others hold to a thoroughgoing eternalism, where all moments are equally real. These readings give almost no distinguishable physical predictions. They're more a matter of metaphysical taste. But behind them lurks a ghost that gives cosmologists headaches. If space-time is large enough and lasts long enough, then by pure random fluctuation, it would occasionally assemble a brain, complete with memories, the so-called Boltzmann brain. Any good cosmological theory has to be able to explain why we are not such a random fluctuation. Here we have to add a crucial piece, called decoherence. A quantum system is never truly isolated. The instant it entangles with a vast environment, the phase relations that produce interference scatter into that environment and can't be recovered. Zurek calls this einselection, and it is exactly what picks out the stable, localized pointer states that make the macroscopic world look classical, with definite positions. It even, in passing, explains why the macroscopic world is irreversible. But note, honestly, decoherence explains why we don't see interference and why a preferred basis emerges. It does not explain why a single measurement ends with one definite outcome. That choice of outcome is still the unsolved measurement problem. What's more troubling, even time itself holds a different status in the two theories. In quantum mechanics, time is an external parameter, not even an observable. But when you try to quantize general relativity canonically, you get an equation called Wheeler, DeWitt, the Hamiltonian operator, acting on the wave function of the whole universe equals 0. Notice, there is no time in that equation at all. The fundamental state of the universe is frozen, not evolving. So where does the flow of time we so vividly feel come from? A beautiful idea called relational time. In a universe that is globally static but internally highly entangled, you pick out one subsystem and treat it as a clock, and the rest, relative to that clock, appears to evolve. Time is read off from the correlations of entanglement. And on this, there's a genuine, currently undecidable disagreement. Ravelli's camp holds that time is emergent, perspectival. Smolin insists time is fundamental, and the block universe has led us astray. So, has it all already happened? Under the block universe reading, in a sense, yes, but remember, that's a philosophical reading of a confirmed relativity. Physics constrains the structure of time, not whether it flows. The third question, that cause before effect we trust most of all, does it actually hold? In relativity, causality is written into the geometry of spacetime. Every event has a light cone, and only events inside it can be causally linked. No signal outruns light. Even entanglement's spooky action at a distance, break Bell's inequality though it may, cannot transmit any information. That's the rule called no signaling. So at the macroscopic level, causality is rock solid. But over the past decade or so, quantum information opened a crack in the very ardor of cause and effect. Picture a device called the quantum switch. You have two operations, A and B, and a control qubit puts them in a superposition of A before B and B before A. Note, this isn't that you don't know the order. The order itself has no definite value. Such a process is provably causally non-separable, and it has actually been built in optics labs, even yielding measurable advantages in communication and metrology. The process matrix framework behind it reveals something deeper. Quantum theory, in principle, allows process structures more general than fixed-order circuits, but here we slam on the brakes. Hard. These experiments are in flat spacetime, treating order as a controllable quantum degree of freedom. It does not mean that fundamental spacetime itself has lost any definite causal order. Extrapolating from a lab's superposition of causal order to the universe's causality is fake is a leap far too large. And by the way, on the gravity side, there's still an open conjecture, chronology protection. Hawking suspected the laws conspire to forbid closed time-like curves, that is, to forbid time travel, but it has never been proven. Honestly, the lab phenomenon is confirmed. What it means for fundamental space-time is an open conjecture. Now we enter the most thrilling, most frontier part of this episode. We ask a more radical question. Is spacetime itself the real foundation? Or is it too something that emerges from a deeper layer? The story starts with black holes. A black hole has a temperature and an entropy. The Hawking temperature is inversely proportional to its mass. In that famous Bekenstein, Hawking entropy equals the horizon's area divided by 4g. Notice area, not volume. This formula is the first place gravity, quantum theory, and thermodynamics collide profoundly. Before black holes, let's kill one intuition. The so-called vacuum is not nothing at all. The vacuum in quantum field theory is a seething, ever-fluctuating state. The cleanest evidence is the Casimir effect. Two uncharged metal plates, simply by excluding some of the vacuum modes between them, actually attract, and that force has been precisely measured. There's also the Unruh effect. An accelerating observer feels themselves immersed in a warm bath of particles. The vacuum has structure and energy. Remember that. It's the backdrop to everything that follows. Hawking found that black holes, because of quantum effects near the horizon, slowly radiate and evaporate. But this brings a catastrophic contradiction. A pure quantum state falls into the black hole and ends up evaporated into completely thermal, mixed radiation. The information is gone. And that violates quantum mechanics' most basic property, unitarity. This is the black hole information paradox. By the way, a real black hole's Hawking radiation is far too faint to have been directly observed. The acoustic black holes built in the lab from Bose, Einstein condensates only confirm the kinematics of the mechanism. They're not real black holes. So how do you tell whether information is lost? Watch a curve called the Page curve. If information is truly conserved, then as the black hole evaporates, the entanglement entropy of the radiation should rise. Then, after a point called the Page time, turn around and fall back to zero. But Hawking's original calculation gives a curve that only rises and never returns. And that is the heart of the contradiction. From 2019 to 2020, things broke open spectacularly. Physicists found that semi-classical gravity itself, if you compute it carefully enough, gives exactly that correct unitary page curve. The key is a thing called the island formula. In computing the radiation's entropy, you must include, inside the minimization, a region inside the black hole called an island. In the gravitational path integral, a new kind of saddle point appears, the replica wormhole, connecting the black hole's interior to the radiation outside. Once past the page time, that island enters the radiation's entanglement wedge, and the information, in principle, comes out with the radiation. But here, we must be honest. This result proves that semi-classical gravity can reproduce that unitary entropy curve, already one of the most important advances of the decade. But it does not tell us how the information physically escapes bit by bit, and most of the calculations live in idealized, two-dimensional, negatively curved models. It solves the entropy, not the whole paradox. Still, it points to a bigger picture, the center of gravity of theoretical physics this past decade. Spacetime may be sticked together out of entanglement. The cleanest model is 8S CFT. A higher dimensional spacetime with gravity is exactly equivalent to a quantum field theory, with no gravity at all, living on its boundary one dimension lower. The Ryu-Takayanagi formula is even more direct. The entanglement entropy of a region on the boundary equals exactly the area of a minimal surface in the bulk divided by 4g. Entanglement is geometry. Van Ramsdonk put it more bluntly. Pull the entanglement out from between two regions, and the spacetime between them is torn apart. Add the bold ER equals EPR conjecture, that a pair of entangled particles and a wormhole connecting them may be two descriptions of the very same thing. Stitch entanglement, geometry, and quantum error correcting codes together, and you have the most dazzling conceptual leap of the decade. But every place all this holds rigorously is anti-de Sitter space, with negative curvature, unlike our accelerating, expanding universe. Carrying it over to flat space, celestial holography is still only halfway there. And that quantum chip experiment hyped a few years back as making a wormhole was later shown to be overread. So the most honest label is, as mathematics, it is rigorous. But to say, this is how our universe came to be, that is still a conjecture. This thread, maybe spacetime is emergent, gets echoed from a completely different direction too. Computing how two particles collide and scatter off each other used to take countless Feynman diagrams. Yet people found that certain such probabilities equal exactly the volume of a pure geometric object called the amplituhedron. And in that language, locality and unitarity are no longer assumed up front, but merge as results. Add ideas like complexity equals volume from holographic complexity, and more clues hint at the same thing. Spacetime, and even quantum mechanics itself, may not be the bottom layer. They may be derived from something more primitive. And holography is, of course, not the only road. Quantum gravity is better seen as a set of competing research programs. String theory is the mathematically grandest. The graviton drops out of a string's vibrations for free, but it has a landscape problem. Compactification yields an astronomical number around 10 to the 500th of vacua, each with different low-energy physics, so it's hard to give a unique prediction for our universe. Loop quantum gravity instead quantizes geometry itself, making area and volume discrete and quantized, and predicts the Big Bang was a big bounce. Beyond these, there's asymptotic safety, causal dynamical triangulations, causal sets, each gnawing at the same hard bone from a different angle. Among all these programs, not a single one has, to this day, been experimentally confirmed, which is precisely the most honest state of this field. But one new trend is worth remembering. People are designing tabletop experiments, getting two mesoscopic masses to become entangled through gravity alone. If gravity really can entangle them, that means gravity, in an operational sense, cannot be entirely classical. Quantum gravity is slowly moving from untestable in principle toward a more hopeful middle ground. Pull the lens out to the largest scale. the whole universe. We have an extraordinarily successful standard model called lambda CDM, a universe described by the Friedmann equations, expanding from a hot Big Bang about 8 billion years ago. The Planck satellite has measured the cosmic microwave background to sub-percent precision, and it fits everywhere. But it also tells us a humbling fact. Ordinary matter is only about 5%, dark matter about 27%, dark energy about 68%, which means 95% of the universe. We can weigh it, but we cannot say what it is. Now that we're on expansion, we have to answer a particularly baffling question. Why do distant galaxies recede from us faster and faster, some even receding faster than light? Doesn't that break relativity? The key is this. Those galaxies aren't racing through space. The space between them is being stretched. That's what metric expansion means. A galaxy's recession speed equals the Hubble constant times its distance from us. The farther it is, the faster it goes. So once a galaxy is far enough, past about 14 billion light years, the Hubble radius, its recession speed naturally exceeds the speed of light. So does this break the rule that nothing can go faster than light? The answer is no. What special relativity really limits is local speed, the relative speed of two objects passing each other, or of a signal in transit. That can never exceed light. But recession speed isn't this moving through space kind of speed. It is the sum of a great stretch of space being expanded, piece by piece. No object actually overtakes light past you, and no information is sent faster than light. And here's an even more counterintuitive fact. Most of the distant galaxies we can see today were already receding faster than light at the moment they emitted the light we now receive. And dark energy is making this expansion accelerate, which means the farther galaxies recede ever faster, and one by one they redshift, dim, and slide forever beyond our horizon, never to be seen again. The evidence for dark matter is many-pronged and very hard. Galaxy rotation curves, the offset between mass and gas in the bullet cluster, the acoustic peaks of the microwave background, yet decades of direct detection on the ground have come up empty again and again, with the most sensitive experiments now nearing a natural floor called the neutrino fog. Meanwhile, cosmology has another famous crack, the Hubble tension. The expansion rate inferred from the early universe is about 67.4. The rate measured with the nearby distance ladder is about 73, a gap of 5 to 6 standard deviations. And JWST has, at 8 sigma, ruled out it's just a measurement systematic as the easy way out. More exciting still is dark energy. In 2024 and 2025, the DISY survey measured the baryon acoustic oscillations across tens of millions of galaxies and quasars, and the result suggests dark energy may not be a fixed, constant lambda, but something evolving with time. The significance of the deviation from a constant is, with DISI plus the microwave background, about 3.1 standard deviations. Adding supernovae, it reaches 3 to 4. Note my words carefully. This is a strong hint, not yet a discovery. But if it holds, it would be wildly interesting, because it echoes a conjecture from string theory's swampland program that a stable, positive vacuum energy may simply not be allowed by quantum gravity, and dark energy must be dynamic. Speaking of vacuum energy, here's a number that might be physics' single greatest embarrassment. Estimate the vacuum's zero-point energy with quantum field theory, and the result is about 120 orders of magnitude larger than the dark energy density we actually observe. This is the cosmological constant problem, the most spectacular mismatch between theoretical prediction and observation in all of history. It's a reminder about the vacuum and about how gravity actually sees energy. We must still be missing something utterly fundamental. I should stress, these cracks do not mean lambda CDM is about to collapse. Quite the opposite. This is productive tension, an extraordinarily successful core framework, plus a few stubborn anomalies that may point to new physics. Take that so-called S8 tension about how clumpy matter is. from a couple years ago. As the analyses improved, it basically eased, and now looks mainly like a systematic. So the real suspense is, among these tensions, which will harden into new physics and which will dissolve into systematics. And that is the most fascinating thing about this field right now. Push back further to the very first instant, and there's inflation. It elegantly explains why the universe is so flat, so uniform, with even the spectrum of primordial perturbations matching. But its decisive proof, the B-mode polarization left by primordial gravitational waves, has still not been found, with the upper limit pressed down to R below 0.036, squeezing out a whole crowd of models. And a byproduct of inflation is the multiverse. Eternal inflation keeps blowing off new bubble universes. Careful here, the multiverse is actually several completely different ideas. Inflationary bubbles, the string landscape, the branches of many worlds, Tegmark's mathematical universe, and their shared soft spot is testability. So they sit somewhere from conjecture to philosophy. Finally, two more facts the standard model can't explain, for the record. 1. Our universe is almost all matter, almost no antimatter. The Big Bang should have made equal amounts, yet the CP violation in the standard model is far too small, so there must be new physics hiding behind it. 2. Neutrinos have mass, the only phenomenon beyond the standard model that experiment has nailed down. In 2025, the Catron experiment pushed the upper limit on the electron neutrino's mass below 0.45 electron volts, while cosmology constrains the sum of the three neutrino masses to within about 0.12 electron volts, closing in on, and perhaps soon ruling out, one of the mass orderings. You see, even this most mature piece, its edges are all cracks too. All right, now to that most famous and most often mangled question. Could we be living inside a simulation? Let me set it straight first. The serious version of this hypothesis has nothing to do with reality occasionally glitching, like there's a bug. Its real force comes from a very cool-headed logical argument. This is Bostrom's trilemma from 2003. He proved that at least one of the following three is true. First, almost all civilizations go extinct before they can run high-fidelity ancestor simulations. Second, almost no advanced civilization is interested in running such simulations. Third, we are almost certainly living in a simulation. Notice, this argument does not conclude we're probably simulated. It says only that one of the three must hold, and we don't know which. Calling it scientists proved we're probably in a simulation is a flat-out misreading, and this whole argument rests on a very heavy assumption. The substrate independence of consciousness, that subjective experience can be realized on a sufficiently detailed computer and need not depend on biological neurons. That is a contested position in the philosophy of mind, not a result of physics. If consciousness happens to need something a digital computer can't provide, this counting argument collapses on the spot. Later, Kipping reran this trilemma with Bayesian methods. Under a neutral prior, the posterior probability that we are simulated came out just under 50%, meaning today, the scales tip ever so slightly toward we are real. But he has a sharp conclusion that's often overlooked. The moment our civilization line builds even one conscious simulation, the scales swing decisively toward we too are simulated. In other words, we're probably real depends precisely on such a simulation never being built. So, can it be tested at all? Right now, the only serious, falsifiable proposal comes from Bean, Davuti, and Savage. If our universe were computed the way we today simulate the strong force on a lattice, a finite cubic grid of spacetime, then that discretization would leave fingerprints. For instance, the highest energy cosmic rays would show a faint anisotropy aligned with the lattice's axes. It sounds cool, but there are two fatal buts. First, it assumes the simulators used a hypercubic grid. Switch to any other grid, and the signal is erased. Second, so far, nothing has been detected. And more fundamentally, this hypothesis is, in general, hard to call science. Any discretization scheme tends to break Lorentz invariance. Exactly the symmetry experiment has confirmed to extreme precision. And you can't, like a video game, only render where someone's looking, because nonlinear dynamics couple large and small scales tightly together. As for those papers claiming to have proved the universe is not a simulation, like the work of Ringel and Kovry-Shin, they really only constrain one specific classical Monte Carlo method. They don't touch the general question at all. A few more odds and ends, mainly so you don't get fooled by them. Some people, like Vopson, claim a so-called second law of infodynamics, hence the universe is simulated. That's a fringe view, not accepted physics. Its core law is essentially a restatement of the already known thermodynamics of information erasure. Others estimate from energy and information that truly simulating a universe like ours would cost almost impossibly much. Take these as entertainment. So how do the philosophers see it? Chalmers offers a surprising angle called simulation realism. Even if we are in a simulation, the world is still real, not an illusion. Tables and chairs still exist, only they're made of bits rather than quantum fields all the way down, and your life still has meaning. So the simulation hypothesis is really a metaphysical hypothesis about what reality is ultimately made of, not a skeptical one that nothing exists. One last clarification. Physics does contain a serious family of information-first ideas. Wheeler's it from bit to Hooft's cellular automaton interpretation and the it from qubit program we met earlier. But they all speak of the structure of the world, with no external programmer assumed. So, the most honest conclusion is, the simulation hypothesis, in its general form, is unfalsifiable. In its narrow, falsifiable form, it has so far found nothing, which means, as usually stated, it is not a scientific claim about our world, but a legitimate and genuinely interesting topic in the philosophy of physics. Right about here you might be thinking, this assumption that consciousness can run on a computer? Is it just hot air? As it happens, in March 2026, a company called Eon Systems publicly announced they had uploaded a fruit fly. They took that famous whole brain connectome of the fly, a complete wiring diagram of about 140,000 neurons and 50 million synapses, put a simplified firing model on each neuron, and connected it to a virtual fly body inside a physics engine. And then this digital fly really did start on its own to walk, to groom its antennae, to forage for food. Behavioral agreement, they said, 91%. First, in fairness, this is, in itself, no small achievement. For the first time, someone stitched a connectome, a vision model, and a physical body into a closed loop. Sensation in, neural activity propagating, then driving the body. It's a genuine convergence of connectomics and embodied simulation. But the trouble is hidden entirely in that one word, uploaded. Look closely, and a string of problems surfaces. This system is assembled from several already published public models. The walking uses gate controllers, someone else trained long ago. The vision, for now, is basically decorative. Between brain and body, only a handful of descending neurons are wired up as handles. And that neuron model has no plasticity, none of those slow-acting chemical signals, and no glial cells, which make up half the brain, so it can't learn anything new and can't form any memory. Not to mention, the fly's body was never even scanned, so the real motor neurons were never connected. As for that 91%, it was never publicly defined, and there's no paper, no code, no third party that can reproduce it. And the deadliest blow comes from a control experiment at the University of Washington with a brilliant name, the Digital Sphinx. The researchers took that same fly body and wired it to a totally unrelated brain, the connectome of a roundworm with just 302 neurons, and trained it hard with deep reinforcement learning. The result? This worm-brained, fly-bodied chimera walked with just as convincing, just as beautiful a fly gait. The conclusion is cold and clear. Realistic behavior does not require correct biology. The body, plus the physics engine, is itself a powerful filter. Almost any control network can be tuned to produce a decent walk. So that lifelike quality you see in the video proves nothing about whether the fly connectome's biology is doing the work. So, if one day this were truly accomplished and rigorously validated, what would it mean? It would mean a mind really can be rebuilt from structure plus dynamics on a different substrate, which is exactly the load-bearing stone shared by the simulation hypothesis and uploading the mind. And it lands right on Kipping's line. The moment we build even one conscious simulation. But hold it up to our 3-layer ruler and it all becomes clear. The connectome plus closed-loop demo is confirmed. Whether the behavior is truly driven by the connectome's biology is a hotly contested conjecture. And whether it has consciousness, whether it counts as an upload, is purely philosophy. Eon itself says this fly is conscious in a limited sense, yet it can't form a single memory. So you see, this is a perfect live drill. Next time a headline like, "We uploaded a fruit fly," comes crashing down on you, you'll know how to take it apart steadily into those 3 layers. Here, let's step back. Physics today sits in a strange place. We can use 2 theories that contradict each other at the foundations to predict with staggering precision almost everything from particles to galaxies. We can weigh the whole universe to the gram, yet can't say what 95% of it is. We stand on a patch of extraordinarily solid known ground, ringed all around by the deepest unknowns. Those 4 late-night questions, we can now settle the accounts, layer by layer. The repeatedly confirmed layer, the 2 cathedrals, gravitational waves, Bell non-locality, the Higgs, neutrino mass, and that 95% dark universe. The genuinely open frontier, quantum gravity, what dark matter and dark energy actually are, whether space-time emerges from entanglement, whether there's new physics behind the Hubble tension, and the philosophical layer that no experiment can settle, whether time flows, whether the world is deterministic, whether we live in a simulation. Twice in history, our whole picture of reality has been rewritten, once by relativity, once by quantum mechanics. Many believe we may be standing at the door of a 3rd rewrite, a picture in which space-time and gravity both emerge from a deeper layer of quantum information. But unlike the first 2 times, this one hasn't yet been forced on us by a single decisive experiment. And in the next 10 to 20 years, what would count as a historic breakthrough? Roughly these: detecting the B-mode polarization left by primordial gravitational waves, confirming inflation directly; launching a space gravitational wave antenna like LISA, opening the millihertz window; catching a dark matter particle directly; pushing does dark energy evolve from a hint to a 5 sigma discovery; or, on a tabletop, actually seeing gravity entangle 2 objects. If this episode leaves you with just one line, I hope it's this: physics is far better at telling you how to calculate the world than at telling you what it is. And that honest gap between calculation and meaning is exactly the most fascinating thing about being alive right now. So the next time someone opens with "science has proven" and tells you the future is already destined, or that we live in a simulation, you'll know to gently ask, is this confirmed? Is it still conjecture? Or is it pure philosophy? See those 3 layers clearly, and you are already closer to the truth than almost everyone else. That's all for this episode. See you next time.